Okay, thank you, Cleo. Thanks for introducing me. As Cleo said, indeed, I will talk today on the companions and the shaping of the winds of evolved stars, but my last slide is on planets, so I will make the bridge there. I have taken this opportunity also to introduce our master students a bit to the topic. So you will see that my talk is split up in two main parts. And in the first part is really meant to get our master students and also people not from this field to get them on board on the main question that we try to tackle with this research. Since with this research, what we are aiming at is we aim to understand a lot of phenomena. If we are not talking about the chemical enrichment of the universe, the mass spectrum of planetary nebulae, white dwarfs, or gravitational wave progenitors, the frequency distribution here of the supernova and the supernova type 1, type 2, or if you're talking about the fate of exoplanets. These are all phenomena which are highly regulated by the amount of mass that stars lose throughout their life, and in particular, the mass that a lot of stars lose when they're old. So we talk here about cool aging stars. So in particular about asymptotic giant branch stars and red supergiant stars. So you should have seen that, the master students, in the classes of Connie. And so these cool aging stars are key agents regulating a lot of phenomena that you can see here. But they're also more than that. I also like them, or to call them, key physics objects. Key physics objects for various reasons. So you see here that I've written their key physics objects for what I like to call deterministic and conceptual questions in the broad field of astrophysics. So the deterministic aspects really seeks to answer the how question. How and how much do these cool aging stars contribute to the galactic chemical enrichments? And given some initial conditions at birth, in what way can these evolved stars determine the evolution of a galaxy? What kind of atoms, how many molecules, what type of molecules, what kind of dust grains do they form? How are these winds and these mass loss rates generated? The conceptual aspect is more general, and it tries to address this overarching why question. Why do cool aging stars contribute to the galactic chemical enrichments? And this question is posed in the sense of identifying the general physical and chemical laws and their interaction. And these laws are not only applicable to these cool aging stars, but to all of astrophysics. Indeed, we are convinced that the laws of physics and of chemistry are universal laws, but we must also admit that our knowledge of chemical processes is still very Earth-centric. And as I will discuss today, these cool aging stars are really unique chemical laboratories, which offer us this exquisite possibility of teaching us about extraterrestrial and hence universal chemistry. So understanding the crucial role of these cool aging stars for that conceptual question maybe still ask for a little bit more background. Since although not always recognized, these stars deserve this critical status exactly because they were thought to be simple. And for some people, simple means also boring, but I will show you that this is not true. Simple since the first identification of these stars by Miss Maury in 1897 already, and then the further classification of these stars in the Hertzsprung-Russell diagram, as you know, by Hertzsprung somewhere between 1905 and 1911. These stars, and then later on also their stellar winds, were thought to have an overall spherical symmetry, and hence they could be described by simple one-dimensional equations. And then they were simple, their thermodynamical structure, simple one dimension, and in their stellar winds, we know that that they generate a lot of molecules, a lot of atoms, and a lot of dust grains. And that is exactly why these stars are such an ideal candidates for unraveling the general physical laws, the general chemical laws, and the details of their interaction. They are really this exquisite extraterrestrial laboratories. But as you will hear today, there is a challenge, and I here call it the 4D challenge. Since groundbreaking observations and theoretical insights, new numerical simulations and laboratory experiments, they bear ample of evidence that our notion of these spherical stars and spherical winds was oversimplified. These cool aging stars, you know, have an incredibly rich life in 3 dimensions. We see that they have 3D complexities that bridge 23 orders of magnitude, so from the nanometer scale up to the astronomical unit scale. And so we need to embrace and understand these 3-dimensional spatial realities if we aim to quantify mass loss, if we want to understand its effects on stellar evolution, and hence if we want to drastically improve our predictive power of the evolutionary path in this 4-dimensional classical spacetime. So let's first set this 1-dimensional stage, and then I will show where the complexity arises. So this is just a schematic for people who have never seen that, of this AGB star in yellow, and then several spatial regions in the stellar winds. So you can see, and shown here with these arrows, is that AGB stars, and to a lesser extent also with supergiant stars, they are pulsating. And due to these pulsations, we have shocks in the inner winds. And the consequence of these shocks is that we have a chemistry which is out of equilibrium. Further out, where densities are still high enough, but temperatures low enough, these molecules can form larger gas phase clusters and form dust grains. And then it's exactly then the radiation pressure on these dust grains that generate the stellar winds, and also the fact that these dust grains are coupled to the gas. So we get here, as of this blue region roughly, the initiation of the stellar winds. Further out, where we have then the steady outflow, we have also a lot of other very interesting chemical processes that take place and that continuously create a new assembly of molecules and dust grains. And so we aim to understand this whole picture. Now, aiming to understand this, as you know, comes from different perspectives. And so the first person who has ever used observations to give us a mass loss rate prescription for this kind of stars was Reimers in 1975. And this mass loss rate prescription, so the mass loss rate is in dots, you can see is proportional to the luminosity and inversely proportional to the gravity and the radius of the star. Eta is a unitless parameter of the order of unity, and this is then a scaling parameter. Reimers has done that for its supergiants that were in a binary system. And this was the first prescription, and as you know, people are using this kind of mass loss rate prescriptions in stellar evolution modeling. This prescription that you can see here is still one of the prescriptions that is most often used nowadays. But that's only one way of tackling and understanding mass loss rate prescriptions. In general, and here again for the master students, there are 2 ways. Let's call them the forward method and the retrieval method. The forward method is more the theoretically oriented method, in which you take into account all the relations, all the physical and mathematical chemical relations, and you make a fully consistent picture. And you use then your theoretical model to make a prediction on the mass loss rate. This kind of predictions, as we all know, can be only as accurate as a model that you're using. So that's one of the drawbacks. You also realize, and you will realize it also later in the talk, is that this kind of computations can be extremely CPU demanding. And as such, they are seldomly used to interpret observations in this kind of a retrieval methods. So when you're modeling observations, you often need to parameterize some of the quantities that you need. These parameterizations are then either based on your theoretical predictions, or they are based on hypotheses that you can draw from other observations. Also, these retrieval methods have their drawbacks, especially if it comes into understanding the biases in your analysis, into sometimes also understanding what are exactly the parameters. And for instance, if you need the luminosity, you need a very accurate determination of that luminosity in your prescription. But these are generally the methods. And you see that, and the whole thing is also is that when people are, for instance, working on these forward models, they tune their outcome sometimes a little bit to what they see from the retrievals. And that's fine, since it are the observations that give us a real answer, but we should be extremely vigilant against any confirmation bias in anything that we are doing. So these forward methods, the advantage of them is that they tell you much better what might be the explicit dependence of the outcome. So here for us, the mass loss rate on some of these parameters. But as you can see here in this picture from Jels, from his PhD thesis, if we aim to model stellar winds, this all kind of processes we need to take into account. So the dynamics, thermodynamics, the radiative transfer, and all kind of chemical processes that are dealing with gas phase molecules and the dust. And that's not a simple exercise. So as of today, there's no code that yet can deal with all of these complexities, also since we often are missing a lot of the input. For instance, a lot of the gas phase chemical reaction rates are unknown. And so for people who are just, I know that some people are scared when they see this equation, but it's very simple. I want to use them to show you only a few aspects. First of all, what you see here is just an assembly of equations that you would need to use if you want to model a stationary outflow. So you do not account for the gray regions here, but you say that you have a mass loss rate that is time independent. And so then you need to solve the equations that tell you about mass conservation, momentum conservation. Here you can see the energy conservation and the first law of thermodynamics. Here you would compute the temperature of the dust grain. Number 5 is then the radiative transfer that you can implement. And number 6 then gives you then all kind of chemical reaction rates and their formation and destruction mechanisms. And so this on sich is a very well-posed set of mathematical equations that given some input parameter. And so for this ones that you can see here, this would be the mass loss, of the star, the temperature, the luminosity, and your set of abundances that given your mathematical model, and I write this here as the double M of this calligraphic M, would give you the mass loss rate, so the theoretical mass loss rate. For instance, if you do this kind of a modeling effort, you can do predictions of the mass loss rate. And so you can see here, and this is a figure that was kindly made by Siddelmeier, is you can see that for this particular input parameters, the mass loss rate would be around a few times 10 to the minus 5 solar masses per year. But what is important also for you to see is if you then see how this red curves, the gas velocity and how the gas temperature, how they behave, you can see, oh, that looks quite simple. They are roughly power laws. Well, this is then exactly the input that is then used for retrieval methods. They use outcome of forward models, this kind of power law approximations, when they are modeling the observations. And so if you then look now to the next slide, for instance, you can use observations of carbon monoxide, the top row, or you can use spectral energy distribution together then with this kind of a parameterizations. And if you do that for a whole bunch of stars, you can also have a retrieval method that gives you, in function of your input parameters, again the same ones as in the previous ones, but now guided by observations, would give you a mass loss rate. And I give you two examples here. You will see them coming back later on, based on this kind of an exercise. Jacob van Loon in 2005 has proposed a mass loss rate prescription, and Goldman in 2017 has proposed another mass loss rate prescription for this kind of stars. And then the attentive listener has heard me saying, this is stationary. I do not account for the pulsational behavior. So how correct are these kind of a mass loss rate prescriptions if you do not see a time dependence there? So let's first take a step back and let's first let you understand what is the cause for this variability. Well, actually, we do not know that yet exactly. There are now already very advanced, even three-dimensional simulations that try to understand what is the physical cause for the pulsations that we see in the observations. It's a combination of convection, the kappa mechanism, potentially also some acoustic noise, but in the end, we are not yet sure. So if we look to observations, you see that these stars are pulsating, and some of them seems to pulsate in the fundamental mode. So I come back to people who are used to astroseismology, and also in the overtone modes. So what you see here, and I really like this figure, it's a figure made by Trabucci in 2019, and it's for a one-dimensional pulsation model, and it only codes from the linear pulsations. And so you see here, it's a function of time on the AGB, and the color code shows you which of the either the fundamental, the first, the second, or the third overtone mode is the dominant one. The bottom part is the growth rate, and here you can see the pulsation period. The pulsation period, I've written it here to the right, is linked to the imaginary part of the pulsation frequency. And so what you can see here, and just follow my cursor, is that you can see that at the beginning of the AGB's phase, the stars are mainly pulsating either in the third or the second overtone mode. And as time evolves, you see that they go to lower radial modes, and finally they reach here the fundamental mode pulsation. Stars that are pulsating in the first overtone, second overtone, you will often hear saying they're semi-regular variables, since you see that they're often not only pulsating in one, but then in various modes. Stars that are dominantly pulsating in the fundamental mode, they are Mira-type variables. And you see that as time evolves, the pulsation period increases. And also as time evolves, the luminosity increases. And this is very important for you to understand. So the luminosity increases, we will have more photons, and you will see that also in the next slide. This will also induce an increase in the mass loss rate. And this is what you actually will see in the observations. So I come back now to an observational plot. You see here the period at the x-axis, and the y-axis is an approximate equivalent to the mass loss rate. And you see here that there is some rapid increase around the pulsation period of 60 days. Then there is some increase between 60 and 40 days. And then beyond that, you see a very rapid increase here in the mass loss rate. You can see it even better in this slide. So you follow my cursor. You see here that beyond these 300, 400 days, you see this incredibly increase in the mass loss rate from a few times 10 to the -7 to almost 10 to the -4 solar masses per year. And so we think that if these stars are pulsating in a fundamental mode, so very regularly, they have time enough to create the molecules in the dust grains. These dust grains are a little bit destroyed by the next shock wave, but at least they have time enough to grow inside and as such trigger the wind and hence also create the circumstellar envelope. And so if we are now looking to these forward methods, and now I come back to the theoretical way of dealing with that. I'm saying, okay, they're pulsating. So what do these theoretical methods then tell us upon mass loss rates in function of time? And so there exist methods, and one is currently really improving on that. The most simple method is what we call the one-dimensional episton method. So you just have your inner boundary and you let it pulsate. It's a method that is mainly designed to mimic fundamental modes pulsators, so these Meyer variables. Recently, also a much more advanced method has been developed by Freitag and Susanne Höfner. One is not yet at the stage of creating grains, but they are already dealing with this very convective, unstable upper layers. And so what is now happening if I'm using that knowledge and I try to create mass, and I try to predict mass loss rates in function of time? Well, this has been done by only 2 or 3 authors at this moment. And so if you then have a mass loss rate in function of time, so you again have here the same quantities that are your input parameters, but you also have your pulsation period and the shock strength, for instance. And you see here one of these fits towards the outcome. So that's just a linear multivariate regression analysis of the outcomes. And so you see here the mass loss rates as written as a function of these input parameters. But what should take your attention are these regression coefficients. They are quite high. They are high for the first parameters I show with my cursor, but the ones that I now have indicated in red, they have very low regression coefficients. So this implies that you can have a reduced fit with an equally high correlation coefficients in which I do not take these last factors into account anymore. And so this was for a grid of models for carbon-rich stars, and I've done the same exercise for a grid of models published for oxygen-rich stars. And you can see here as well that you have a fit to the outcome, which in both of these 2 last equations, you do not see anymore an explicit dependence on time appearing anymore. The time dependence is there, but it's implicit in the sense that, sure, when you have your pulsations, this will change the density scale height, and as such, you will have a more efficient condensation and growth of the dust species. But just from a fitting to the outcome, it's not explicitly there anymore, that time dependence. And that is exactly why this observationally driven mass loss rates prescriptions, they seem to do a good job also by not accounting for this explicit dependence on the mass loss rates. So here I show that again for the Reimer's law, the one with which I have started. But now comes a problem. If I'm now comparing various kinds of mass loss rate prescriptions that have been derived, both from observations and from theory, this is what you see. And so what I've done here for this plot is in the dashed lines are theoretically predicted mass loss rate prescriptions. The full lines are observational ones, and the dashed dotted lines are semi-empirical ones. So they use a bit of observations, but also some theoretical input. The blue shaded region is the region where the mass loss rate is above the nuclear burning rate of hydrogen in the car. So that's the thick black line that I indicate here. So whenever you're above, it is the wind mass loss rates that determines evolution. Whenever you're below this black line, it is the hydrogen burning rate that is more important. And so you see, that for the same regime, you see mass loss rates that can differ by orders of magnitude for these AGB stars. And not only for these AGB stars, the same holds for these red supergiant stars. So I started my explanation saying we need to understand the mass loss rate through time if we want to have reliable predictions on stellar evolution, if we want to understand the chemical enrichment of the universe, if we want to say something of the gravitational wave progenitors. But how can we say something which has a high reliability if we are facing this problem? So this implies we need to understand that problem. And I just show you here the impact of not understanding these mass loss rates. You can see these are just very simplified stellar evolution calculations. But for an AGB star with an initial mass between 0.8 and 3 solar masses. And for each of the several plots, I just have used another mass loss rate prescription. And you see what is the different color codes. So the stars is just indicating what is the mass loss rate at that stage. So I've indicated something in green when a mass loss rate of 10 to the minus 8, some masses of the year is reached, and then yellow 10 to the minus 7, and so on. And the full red dots here are just where you change from the nuclear burning rate regime towards a regime that the wind mass loss rate is more dominant. And so you can see that when I would focus on these two ones, Fasiliadis and also Blöcker, are quite often used also in stellar evolution models. You see that you have a kind of an asymptotic regime. You have first quite horizontal, and at the moment they reach here this part, it's called the cliff by Lee Anna Wilson. They asymptotically go downwards. And it is the fact that you have this cliff behavior, if that would be true, that also gives you a very strong selection in your observations. Since stars that are not yet near the cliff will have low mass loss rates and so are very difficult to detect in the observations. But stars that pass beyond the cliff will be very short-lived and will also cause a scarcity in our detection rates. And so that is why, and I really found it very nicely formulated by Lee Anna Wilson, that she's saying, you know, this mass loss rate, and especially these empirical mass loss rates, they tell us the parameters of the stars that are losing mass, but they do not tell us the dependence of the mass loss rates on the parameters of any individual stars, or they cannot tell us how stars are losing mass over time. And so, and you could hear it already from the start of my talk, it is the fact that I think we are still dealing or thinking or often modeling these stars as being, of the stellar winds as being one-dimensional, that this is really the problem, and that gives us a very problematic framework. As you will see, and as I will talk about today, so I come slower, I will start now almost in the second part of the talk. It is the fact that we have these three-dimensional complexities that we should understand if we want to have a reliable predictions of the mass loss rate in function of time. And I'm talking about three-dimensional life of molecules and their dust grains. These are things that, for instance, David is focusing a lot on. How can we understand that? It is understanding how clumps that are generated by this convection, how that impact our understanding of the mass loss rate. So this is also work by Michael and by Emily. And here also then the last aspect, how can a companion, a binary companion, impact any diagnostic of our mass loss rate? And this is then the work on which I will now also focus today. So we need, and I come back to the start of my presentation, we need to have better predictions of the mass loss rate, 3D predictions, 3D understanding in function of time, if we want to have better predictions of each of the facets that I show here at the bottom of the slides. So today, and now the second part of the talk, I will only now focus on one of these aspects. The other ones are equally important, but together with the people of the ATOMIUM consortium, we have been working on that latter aspect a lot, and it was a very nice consortium to work with. So I start this second part with a little bit of history. And so we go back almost one century ago. And so when the first photographic atlas of planetary nebulae has been published. So for the master students, AGB stars, when they have shed off most of their stellar winds, they will go back to the stage that their temperature will increase, and then the UV photons will illuminate the stellar winds. And that's the stage that we call the planetary nebulae phase. And in 1918, Curtis has then published this first photographic atlas of this planetary nebulae, and you can see that he could see a lot of morphologies that were highly different one with respect to the other. And it lets him wonder the following: if it would ever be possible to postulate any general form or forms which shall be mechanically plausible, and to which the planetaries, or a considerable proportion of the planetaries, will more or less closely conform. Since this was really a challenge, you know, observations of these AGB stellar winds have shown that this overall morphologies of these stellar winds, for 80% of them, it is a spherically symmetric morphology. And then we come to this planetary nebulae, and then depending on which fraction of what kind of planetary nebulae that you're looking at, less than 20%, and even some people claim less than 4% of this planetary nebulae are spherically symmetric. So how can we explain this transformation? So several causes, several hypotheses have been offered. For instance, they include a rapidly spinning of the star itself, or strongly magnetic fields have been proposed, but also these two mechanisms have been questioned, since it's very tough then also to maintain this very strong asymmetries. And more recently, binarity has been proposed, but with a very specific focus. It is binary companions that have a very short orbital period, and as such, that have a common envelope phase. So this is fraction E here that I show here from this figure of Rob Isert. I come back to that stage. So you should just envision that these stars are so close to each other. They are very rapid, they have a very short orbital period, and they have some kind of a common envelope around them. And then you can easily understand that this kind of mechanism can create very strong asymmetries. And here is where, there it is, where ATOMIUM comes into the picture. This is a little movie that was made by Maarten Hikiere. It's really fun. And so what does ATOMIUM, what does our consortium has found on that particular aspect? And I immediately show you, this is one of the figures that we have been published, or that we have published recently in September in the science paper. And what you can see here is a gallery of the winds of red giant stars, so AGB stars. And if I show you again here this picture of the planetary nebulae, you see here quite a lot of similarities in morphologies between these planetary nebulae and the winds of these AGB stars. So you can see bipolar morphologies, you can see eye-shaped features, you can see regular spaced arcs. Here in these phases, you can also see more kind of a spiral structure. This one we call it, that has a kind of a rose-like structure. Each of these morphologies has some kind of a counterpart also in this planetary nebulae. And this leads immediately to two conclusions. Namely, it is the same physics that shapes both AGB winds and the planetary nebulae. And with this AGB phase, we catch the mechanism while it is in act. Since what I forgot to tell you when I was discussing with you on the different causes, well, that could create this planetary nebulae, well, most of these causes, you know, they act on the star itself, and they were thought to only happen at the extreme end of the AGB phase, but most often during the post-AGB phase of the planetary nebula phase. And here we say, well, that's not true. The shaping already happens during the AGB phase, and not only at that very end or even beyond that end of the AGB phase. So the mechanism is already acting much earlier. And well, then this ATOMIUM project, which I now only have barely introduced to you, that's an ALMA large program. And it's a large program that was granted 130 hours of observational time. And together with some 35 to 40 people in the consortium, we have been working on this data. So we have used the telescope in various setups to observe 17 stars. So you only see here a small fraction of them in a specific wavelength region. And so what you see here is some channels of carbon monoxide, but that's only one of the molecules. We have detected roughly 100 to 200 molecular features in the data. And then we have that for several setups for a lot of stars. So then you start already understanding that it's an extremely difficult exercise upon how will we deal with this enormous amount of observations. It's a few terabytes of observations that we now have at our disposal. And so together with the colleagues, we have been playing a lot with this data, just visualizing things, trying to understand if we could see something in this data. And in the end, one of the things we came up with is a kind of an ATOMIUM decision tree, we call it now. And so we do not only use the carbon monoxide channel maps, but we look also to the velocity profiles that we deduce from the data. So normally you expect that you have low velocities in the inner wind and then that the velocity increases. But you see that there are also stars that do not behave like that. We look also to, for instance, silicon monoxide towards the moment one maps, as we call it. So just for you to understand, for this star, you can see that there is some part that has a pronounced blue shift to the left and a pronounced red shift to the right. And so this tells you something upon the potential of bipolarity, or maybe a Keplerian rotating disk in that star. And I still remember the day that I was working on just looking at this data and making a spreadsheet, an Excel sheet, and trying to understand what I was doing. And I was not doing that in my office. I was working that day in Connie's office, since one was painting here my office. And I was color coding some things since, it was just too much for my brain to just keep track of all kind of information in that huge spreadsheet. And suddenly it took my attention that when I was color coding it, and in addition, when I was classifying or ranking the stars with an increasing mass loss rate, as you can see here, that I also did see a classification in my colors that I was using. We now call them class 1, class 2, and class 3. I indeed had something as orange, green, and blue in my Excel sheets. And you will see in my talk is that these classes have a meaning. Class 1 stars will be stars with a low mass loss rate in which we have a very strong diagnostic towards an equatorial density enhancement. So this is the EDE. Class 2 stars have a very pronounced bipolar morphology, and class 3 stars have a very pronounced spiral morphology. Pay attention, it does not mean that spirals do not have IDEs. I just tell you something upon the prevailing geometry that we see. So the ordering that you could see here in this picture was not random. So it's an ordering with an increasing mass loss rate from left to right and from top to bottom, and which has a very high Kendall rank tau B correlation coefficient. It was Joris Redder who told me how we should compute this kind of correlation coefficients. And so these correlation coefficients tell us that mass loss rate is an important parameter in dictating the outcome of the morphologies that you can see here. So then I come back here to this plot and to the different mechanisms that has been proposed. So of each of these mechanisms, the only one that can easily incorporate the mass loss rate as being dictating or important for the geometry of AGB stars and later on also of planetary nebulae is the bottom one. It is binarity. But you see immediately that I open the picture. It's not only binarity towards binaries which have a short period, but it also includes the picture of having long period binaries, which have a long periods above a year, and which have quite a large separation above 2 astronomical units. And I need to explain you why we say it like that. So I come back to a little bit of your binary classes that you get from IvS and the Roche Lobes. So you can see here you have 2 stars over here, and the color coding just indicates your sphere of influence. And when that sphere of influence are the equipotentials, when they reach each other, so you can see it with my cursor here, this is what we call here the Roche Lobe. And you see it's a bit eardropped in shape, and the point where my cursor is now is the first Lagrangian point. Now, if stars, you also know that the closer stars are to each other, the stronger the interaction will be. So the first one is we have a detached binary system, and sometimes, yeah, there is indeed some kind of a tunneling of material from that star, if it's losing mass, towards the companion via the bounty hole Littleton accretion. If the star is inflating, since it becomes an AGB star and fills its Roche Lobe, you can have a semi-detached system with severe mass loss through L1, and then the point of extreme contact, so contact binary, you can see here in the last part, is then the common envelope phase. But there is a class in between that I didn't show you yet, and that was not taken into account for a long time. And it is this class where it is not the giant star that fills the Roche Lobe, but that it's the wind of the star that fills the Roche Lobe. So we call that class the wind Roche Lobe overflow. And then the wind can tunnel through, or roughly through L1, and can potentially form here an accretion disk. So the first persons who have done simulations of binary interactions, but no, not acting on the star, but acting on the winds, were Mastrodemos and Morris in 1999. And I show you one of the outcomes here. So the first plot is if you would look at it face on. The second plot is if you just turn 90 degrees and you would see the system edge on. And so in the face on view, you see nicely that a spiral structure is arising. And you see here at the edge on view is that the spiral has a quite distinct height. It almost reaches here the orbital axis. And so this is a spiral which is creating by the wobbling of the AGB star around the center of mass. But that's one of the spirals. You can have also a different kind of spiral, and that's the spiral that is attached towards the companion, and it's just from the companion that is attracting, I will show later a better simulation, but it's attracting part of the material of the AGB star, of its spins, and then it almost takes it behind, while it is going around this AGB star. This second kind of a spiral you see here, and its height above the orbital plane is much lower. And you can see here also that you get some kind of an equatorial density enhancement. This was the year 1999. It was also the same year when the first ever multiple incomplete concentric shells have been detected around the carbon star ERC 10-16 by Moran and Huggins in 1999. But I think probably unaware of the results by Mastrodemos, Moran attributed the shells to mass loss modulations with a time scale of 200 to 800 years, caused by an undefined episodic process intrinsic to the star. In the paper, you can see that they made some suggestions then to leave towards a binary companion, but they deemed it insufficient to explain the structure of the shells further out. And you know, that kind of an idea has even been explored in quite detail, one-dimensional models, not accounting for a binary companion, by Yvonne Simis, where they try to understand, can we have just one single star, and can we have this kind of a shell-like structure? It took an additional 7 years before the same author, so it's again Rowan and Huggins, but now in 2006, reported the detection of the first conspicuous Archimedes spiral pattern in the winds of AFGL 3068. This discovery was, and still is in my opinion, very highly significant, since it was for the first time that it led to the unequivocal conclusion that binary interaction shapes the wind of that AGB star, and as such can play a role in carving out planetary nebulae later on. Well, this was the start of that field, and it was ALMA who really has opened up the field of aspherical AGB stars considerably. And you just will see here in this slide some of these recent morphologies of AGB winds. Some have nice spirals, other ones have bifurcated spirals. You see here that we even start to see filaments in the spirals, but we do see more than spirals alone. Some of the structures are much more complex. For instance, if you just follow my cursor, you see here a structure which in the blue appears to the north. And when we go to the red, so the part that goes away, it is towards the south of the main star. So again, this is a kind of a bipolar structure. A bipolar structure that you also can visualize with this kind of a plots. So this is another star, L2 Puppis. You see here that to the east, material is coming towards you, towards the west, it goes away from you. And here you have, we could show that from the data, you have a Keplerian rotation disk around that star. So we have a lot of astonishing information from these observations. And at the same time that we were gathering all this kind of observations, they were also a trigger of developing more advanced binary models for these AGB winds. I will also show you some of these simulations, and you will see that often, but not always, we capture what you can see in the data. So you see here, for instance, I have been talking about these two spirals. So you have here the spiral which is attached towards the secondary, which has a small height above the orbital plane. And you have here the spiral that comes from the wobbling of the main AGB star that has a quite substantial height above the orbital plane. And now I have to thank Jan and Frederik, who have made this figure, since we are finally at this stage, and that's only recently, that we do not only have to look to density plots and think, okay, this is a density, what might happen if I use now a molecule and take into account radiative transfer and opacities. So I will show you now in the next slide a very nice movie that has been made by Jan Bolte and Frederik. And it's a movie in which you first will see the hydrodynamical model, and you will see the main star and the companion, and you will see how they evolve through time. And then you will see they will start tilting the simulation, so you can see it edge on, and then it will go to 45 degrees and then to 90 degrees. And then you will see how that would look like when I show you the synthetic observations. And so for the synthetic observations, this is also then how ALMA works. You scroll through the emission line in our case, and you will see that each of the different parts in the line, you will have another frame here. So that is how you create a channel map. And I'll let you now enjoy that figure. So you see here that through time, the companion creates a very complex structure. You see also that the AGB star is pulsating. These are the ripples that you could see here. Now they start tilting the movie towards higher and lower angles. You can see that here at the top left corner. And now let's have a look at the observations. And you can see here observations at 90-degree tilt, 45, and at the 0-degree. And now they scroll through the line, and you can see that each time you have a different behavior. So let's turn that around. If this would have been my observations, it is extremely complex to do the inverse process, to understand from this kind of complexities and we have many more parameters in our modeling pursuit now to say, if I have these observations, that will have been the binary system that I'm talking about. Spirals are still quite easy. We at least know we find them easy, but the closer the stars are, the more complex the behavior might be. And you do not only have spirals, as I have said already, you can also have the creation of disks. You can have, I will show that in the next simulation, a creation of a disk around the companion, an accretion disk. And if the two stars are very close to each other, you might have the creation of something that looks like a kind of a circumbinary disk. And this is now a simulation that was made by ILIC, also in the framework of the ATOMIUM collaboration. You could see already, but I'll go back maybe a little bit in this, I go back a little bit in the simulation. It's first of all a very complex spiral. It's a very broken spiral. And we will now zoom in. You see here the accretion disk, that's the one in yellow. You see the compressed stellar wind through L1, and you see here the formation of one of these spiral arms. And this is a simulation for an AGB star that has a very slowly accelerating winds. Take that point and need it later on. This very slow, of low acceleration is important, and it will dictate a lot of the morphologies that we see. And then you could say, but if you knew that already, you know, we have the buildup of models, we have the buildup of observations, why has this paper then been published in Science? Well, it is since we have, or we could use the systematic approach of the ATOMIUM observations. We have used the same technique, the same observation setup for the sample of selected stars. And it was that approach that allowed us for the first time to say that this mass loss rate is a very important parameter. And there is more than that. That systematic approach did not then allow us saying, you know, it is binarity, and it's binarity not only short periods, but also long periods. There was an additional step. We could make an important prediction for stellar evolution. But now comes a critical point. It's a point that I have tried to assess already a few times, since how to probe the invisible. I have never told you that I have seen a companion. Most of the companions, with a few exceptions remain invisible to us. Well, if you don't see us, luckily sometimes statistics can help us in trying to build support up of your arguments. So there are two parts in the statistical argument. First of all, we look to the multiplicity factor when these stars were still on the main sequence. I make a distinction between masses below and masses above 1.5 solar masses. And in this table, you can see a compilation of multiplicity factors of a stellar companion, of a brown dwarf, of planets with a mass above 5 Jupiter masses at some orbital separation. And we correct for the fact that we need, or we are sensitive in the observations to some part of the orbital period. Yeah? And then you need to subtract from that some of the fraction that you will lose when the star goes up on the AGB. Some of the planets, some of the companions will in-spiral, and other ones you will lose since they are too far away. We have accounted, we have roughly estimated that we will lose from this fraction some 10–20% during AGB evolution. The second part is then the following one. Since it comes back to population statistics, and it was only a point that I realized quite late in the process, and this is the fact that in all our observations, and it's not only us, but when we're talking about AGB stars, we are selecting stars with a mass loss rate above 10⁻⁷ solar masses a year, since, you know, we need to build up signal to noise. And lower than that, it's very difficult to get observations. But when you then look to stellar evolution calculations, you know, if you look to our sun, when our sun will be on the AGB phase, it will have only a very restricted period when the mass loss rate will be above that limit of 10⁻⁷ solar masses per year. So the chance of finding stars which have a solar mass as initial mass then, yeah, is incredibly low. So the fact that you have that selection criterion gives you a bias in your target selection, and that you have a bias towards stars with initial mass above 1.5 solar mass. But if so, and then I go back to the first part, this implies that not only for our stars in the ATOMIUM sample, but for the majority of stars, which have a mass weight above 10 to the minus solar masses per year, and hence have a wind mass weight that is higher than the nuclear burning rate, they have high initial masses, and hence we postulate that they have on average more than one companion. And then the only step still to explain to you is, but yeah, if they're binaries, how can I understand the fact that I see this correlation between morphology and the mass weight? Well, this step is only a very rudimentary one that I will show you. We are now currently working with Jan and Bart and Silke and Jolien on having very detailed models that show you that. I show you here some analytical approximation just to give you a little bit of a feeling upon how does it really work. And so we have defined a unitless parameter, we have called it Q, and it's a fraction of P of the companion over P of the wind, where this P wind is a radial momentum of the wind material the companion encounters in one orbit, and P comp then is a tangential momentum of the companion. And so this ratio, when it is very high, you have a very large contribution of the tangential component, and so you tend towards EDE. So this, since you need then some part of the material that comes towards the equatorial plane. If this is a very small fraction, then you have this spherical winds, and a spiral is also spherical, since the radial moment or the streaming lines of the velocity are just radial. And so these are very small ones. And so we have calculated, and under several limited cases, how that Q parameter could look like. It's just scaled here the factor 10 to the minus 6. And you see here that it is indeed inversely dependent on the mass weight, and also inversely dependent on the separation, which is something that you expect. And so one more step, we are almost there. We know that. So if we now have a sample of stars with planets and companions, and they have some initial separation, how will that initial orbital separation change along the AGB phase? And I've done several computations. So this is now for an AGB star with an initial mass of 1.5 solar masses. And then black, gold, blue, and magenta are just computations of the orbital separation in function of time for different companion masses. So here we have an initial orbital separation of 2 AU, 4 AU, 10 AU, and 25 AU. And so you can see how that change. I can discuss it in detail. I will not do that. I only want to focus on one thing. This is this bottom one. Since if you look to the frequency distribution of companions, and this is something that Hugues has helped me a lot with, is that you can then show that the majority of companions have an initial separation above 20 astronomical units. And hence, throughout evolution, most of them will widen their orbits. This is important, since this leads us towards the following new evolutionary scenario of AGB morphologies that we now predict, being that along the AGB phase, I've explained you already, the mass weight increases, it rings you a bell. Oh, this helps in getting spirals and less EDEs, but also in addition, the orbit widens. These two factors both leads towards this scenario. That's for early type AGB phase, you have a higher fraction. I don't say it's one or the other, I just speak in terms of fraction, that have a disk, an equatorial density enhancement. And as time evolves, mass weight increases, more of them goes into bipolar structure, and we end with very high mass weights, which are dominated, or which has a prevailing geometry, which is a spiral structure. So if you want to find exoplanets, you have to look here, since this is where they can have most of the impacts. And this scenario, by the way, is also confirmed by observations that were, for instance, made by Pierre Carvalha and Ward Homan. So indeed, it are these low mass weight targets where we can more easily find exoplanets. But I'm not yet finished with my exoplanets, since there is some more points I want to address here. Since one point of your attention is an exclamation marks. The scenario that we predict here is a scenario for oxygen-rich stellar winds. And so the figure you show here, I really have taken the figure that I made for one of the presentations that I've given in Leeds in 2019, February 2019, since I wasn't playing with that idea. And I was just trying to discuss with the ATOMIUM colleagues, you know, there's such a difference. When you have an oxygen-rich winds, it is slowly accelerating often compared to carbon-rich winds, which are very opaque and which have a very strongly accelerating winds. But if you then compare that with the escape velocity in black, yeah, and with values of the orbital velocity, you can see that, you know, this blue one, so the carbon-rich, these particles, they can easily, much more easily escape since they have this large push from the photons. While this oxygen-rich winds, you know, you will see that here in this region where the companion resides, there is much more complex. I will feel much more the interaction of that companion since they just have this very low speeds. Well, I can tell that ideas, but then luckily I have a great team that takes these ideas and turns them into very nice three-dimensional simulations. And so this is something that Ilek has done, and where he has confirmed that, given some of the parameters that we're playing with, that indeed more of these carbon-rich stars will not have this complex EDE, so equatorial density enhancements, so will be mainly dominated by spiral in their winds. Again, I say mainly, I say not never. Yeah? And so that's the overall picture. So we now have a picture that makes a differentiation between carbon and oxygen-rich, and carbon-rich has much more radial winds compared to oxygen-rich. And these oxygen-rich winds, they have much more the tendency to form disks if possible. And having that picture in your mind gives you the possibility to make predictions on the AGB, on the pulse AGB, on the PM. And I will not discuss each of these predictions, but for instance, if I would ask you, give me a prediction if it are carbon-rich or oxygen-rich planetary nebulae that have a disk, I hope that your answer would be, well, oxygen-rich ones, since they have much more the tendency of forming an equatorial density enhancement. We can also explain why detached shells are so nicely circular carbon-rich stars, and we do not find the circular detached cells in oxygen-rich stars, and so on and so on. So there are a whole range of, let's call them phenomena, that were already present in the literature, but that did not have one idea that could explain it all. And so with now having that idea that was generated from the ATOMIUM data, there is a plethora of phenomena that we can suddenly explain in once. But then this mass loss rate, since it is by purpose I have started my talk on this mass loss rates. And I come back here to the simulation of Jan. This is now a simulation where Jan has calculated consistently, given a carbon-rich nature and given the pulsations, what is the mass loss rate if I have a companion? Well, for this model, he has a mass loss rate of a few times 10 to the minus 6 solar masses per year. But now let's take exactly the same simulation without a companion. Yes, this is what you see. You see a mass loss rate, which is roughly a factor of 6 lower. But this is very important, since in all our observations, think back upon our statistics, if I now look to AGB stars, there is a bias in my observations, namely, a lot of them are binaries. So a lot of them for which I have estimated the mass loss rate, this will have been a mass loss rate for a binary system. and not a mass loss rate for a single star system. So each of the mass loss rate prescriptions that have been used in single star evolution models and that are based on observations might have been overestimated. So one of the projects that we are now starting with is, can we please correct this mass loss rate estimates, since they were not only very highly different when I just have shown you these plots, there's also a missing ingredient there, is that we do not take into account that most of them might have a companion. And lowering the mass loss rate is important, not only for the stellar evolution models, but for a whole range of things. I just list here some of these aspects. We all know there will be less matter that will be lost. And if there's less matter that is lost, well, there will be lower enrichment of the universe. And so you can build up all of this argumentation, and you can make this kind of a very nice and complex diagrams. And I will end here, since there is only that end on these exoplanets. So what happens to planets if AGB stars have a lower mass loss rate? Well, it might be a little bit of an academic question, since we all know that Earth potentially will not survive too long. And so there are even estimates that Earth will be engulfed by the sun, even when it's on the red giant branch, so not on the asymptotic giant branch red. Yeah? But so that you need planets which are beyond roughly 1.15 astronomical units, so to be able to survive the red giant branch evolution. But given the fact that some planets survive the RGB phase, what upon lowering mass loss rates? So if we lower mass loss rates, then it's also very obvious that the change of the orbital separation, which scales with that mass loss rate, will be different. And a lower mass loss rate implies a lower rate of orbital widening if occurring, and hence more exoplanets that will experience a catastrophic encounter with the giant mother star due to tidal interaction. And so doomsday will be there potentially earlier than what we hoped for. And I know ending a talk with a doomsday scenario is maybe not a happy ending of a long story, but as the title suggests, it is more of an academic question, and there might be other challenges on our route. But with this academic question, I wish to end this presentation, and then the only thing that still remains me to do is thanking this ATOMIUM consortium, that has been really very pleasant to work with the last few years. And I thank you for your attention.
Thank you, Leen. Let me put my video back on. So if people have questions for Leen, please just write your name in the chat, and then I will call your name.
Leo, should I keep on sharing the screen?
No, you don't have to, unless you think somebody might ask a specific question on a slide, so we can see. So maybe while people are talking about thinking about their questions, I will ask a question, Leen. So you showed both a lot of advancements in let's see, the theoretic modeling, numerical modeling, and the observations. Mm-hmm. Where do you think the main focus should be now as a next step? Should it be getting more data or more of these numerical simulations? Well, what is going to be the biggest driver?
Well, I think my honest answer is really on both. And since, you know, I have just presenting you the outcome of ATOMIUM, but these are only 17 stars. Yeah? And we see that these 17 stars are already much more divergent than what any of our models can predict. But if we aim to really, and then that's my answer, that's to understand AGBs within the binary context. But if I aim to understand that mass loss rate prescription, then the biggest answer will come from the theoretical developments, I think. So that's the two facets of the answer, understanding the morphologies and how it works. But mass loss rate, I think the biggest burden is now on the theoretical developments.
And do you think there's anything stopping you to progress further with the theoretical development?
Yeah, it's just highly complex. So the models that Jan and so on is working with, they take a lot of CPU time, and we have a lot of issues with implementing the chemistry in the model, since chemistry at some point determines and also the computational time. And so these models, they are just highly CPU demanding. Luckily, we have now almost 500 million, I think, of CPU hours at the Dirac HPC computational facilities in the UK for this kind of simulations. And we will need that. And we will also need advancements in artificial intelligence if we ever aim to have a good and a more diverse view of this complex parameter space and its impact on the Nessels weights.
Okay. Miguel, you had a question?
Yes. Hi, Leen.
Hey,
thank you for the. I'm still
hey.
there. Thank you for the nice talk. I learned some stuff. But I had a question came to my mind. So we saw that all the stars have a 3D geometry for the mass loss, but the mass loss rate estimates are coming from 1D assumptions. So do you expect to have very different mass loss rate once we take into account the 3D geometry? And might it change a bit the classification we have in the science paper?
Well, that's a good question. There are two steps in my answer. First of all, some of the diagnostics to get the mass loss rates will really change. And with some, I mean mainly diagnostics, in my opinion, that are based on spectral energy distributions and the analysis of dust grains. Since these dust grains, they are most often analyzed between 2 and 10 micrometers, so they trace quite warm dust grains. But these quite warm dust grains, given the geometries, they often reside in closer to the stars in this equatorial density enhancements. So with these SEDs, we might often have traced more these equatorial density enhancements instead of the densities there, instead of the orbital densities of the wind mass weights. I think the diagnostics that are based on carbon monoxide lines will be less impacted. WART has done some studies on that. And so then it all depends for sure on peculiar fractions in the analysis and one geometry with respect to the overall geometry, but the correction factors that we had there were lower than correction factors that we arrive with for spectral energy distributions. And so then to answer on the science question paper, for that reason, I have opted in the science paper to only include mass loss weights based on the analysis of carbon monoxide lines. Since I know and I think they are less affected by that uncertainty, but even then, yeah, we have to account for an uncertainty of a factor of a few.
Thank you.
Okay, thank you very much. Thank you, Leen, for the seminar. Thank you, everybody, for attending. And I hope to see you all tomorrow for another IvS seminar. Okay, thank you very much.
Okay, bye-bye.
Bye.